Good afternoon, everyone. Are you able to hear me?
Good afternoon. Yeah,
Okay,
I'm
okay,
able to
thank
hear
you.
you.
So, welcome to week 9 of the live sessions on finite element method. I'm your TA, Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IT Madras. So, in the last class, we saw a problem on the beam bending, how to solve that using the element equations that we formulated the week earlier to that week, and then we solved a complete problem on that, wherein we have a symmetry in our problem, and then we divided our problem into two equal halves and then solved that one. And also in the last class, we also saw that how we can formulate the element equations for a plane frame element. Like in plane frame element, at each one node, we get one more additional degree of freedom. That is the actual deformations. That is, it is just the case of bar element plus beam element gives us plane frame element. So in that plane frame element, we'll be again seeing forward what are the things forward. Let me see that in week 8 we had that one. Yeah, here we saw in the week 8 plane frame element. Like it was just a combination of axial deformation, that is the bar element, and another one was beam element. Okay, so we saw these two things, bar element and beam element, and then combined these two things, we got the plane frame element. Then moving forward, we developed an equation, an element equation from a plane frame element which was not inclined to which was having inclination 0 degree with respect to the global coordinate system. So like the plane frame element was like oriented like this only. Here I have shown it here. Yeah, plane frame element was oriented like this only. So what happens if our global coordinate system is like this and plane frame element is like this? It is having some inclination theta. So we have to see those things as well. Like in bar element, we saw a simple bar like this. Then that same bar was inclined with some inclination theta with the global coordinate system. So moving forward, we will see these things in today's class. One more thing is that I have to take this one from here. So this is our plane frame element. This is our plane frame element. Okay. So in this we saw our equation was coming out to be this thing. KL DL is equal to RL. Okay. So we got finally this one. Stiffness matrix and local coordinates. DL is the vector of the degrees of freedom is called the RL. RL is the force vector. Okay. So we had assumed that it is uniformly distributed. It is distributed, it's having uniformly distributed load over it. So we can write an expression for the RL as well. So RL that is can be written as, you can write the no, nodal forces and moments as Fx1, Fy1, M1. Similarly for the node 2, Fx2, Fy2, and M2. These are the things we can write, which is equal to, since it is uniformly distributed load, it will be having following things: 0 QL by 2 nodal force vector, uh, QL square by 2. Similarly here again QL by 2, it's obvious, minus QL square by 12. Okay, this is 12 here. These things we are going to get. Now we have two things. Same thing we are seeing here. We have we have this global coordinate system, x global, y global, global system, and we have the same bar element, not bar element. We have same space frame element. We have space frame element. It is having some inclination. Okay, so it is local coordinate system. We can show it like this. This is its local coordinate system. Okay, it is having an inclination alpha with capital X. These are its global coordinates: x1, capital X1, capital Y1, and here again it is capital X2, capital Y2. These are the things, and its local axis is inclined like this. It will be along its axis like this. Okay, this is small x local. Okay, small x will be like this, and small y will be like this. Okay, y local. Okay, and one more thing, we are assuming it to be loaded with uniformly distributed load. Okay, Q. Mm, the space this plane frame element is having a length of L, so we will be writing it as degrees of freedom. So degrees of freedom will be here U1, V1, and one more degree of freedom will be theta 1. Okay, we'll write it with different color. Okay, theta 1. Same will be U2, V2, and this is theta 2. Okay, these are the things. This is plane frame element. Element inclined at the rate of alpha with respect to global x, global x coordinate system. Okay, so one more thing is there. I want to show you what is the sign convention of the forces that we are going to follow. Forces, actual forces like this, actual forces like this, which are pulling the bar. We are taking these to be positive actual forces. Actual forces, internal moments. Internal moments will be, which will be of this convention. We will be taking them to be positive. Okay, internal moments. internal shears. Internal shears will be acting in this fashion. We will be taking them to be positive. Okay, this internal shears. Positive directions of element forces. Positive direction of element forces. Okay, from the so so I already showed you how in local system it is related. KL is equal to DL is equal to RL. So we have, yep, KL local system, DL is equal to RL. Okay, RL. One more thing is that in the we can transform this DL local coordinates, that is local degrees of freedom, to the global degrees of freedom using the transformation DL is equal to T transformation matrix times the global coordinates. Okay, I showed you in case of truss element. Okay, so you people remember this thing from that one. So I can put this DL here. I have KL times T D D is equal to R local. Okay, okay, R local. If I pre-multiply by T transpose matrix KL times T, like this, D will be there again. It will be T transpose, it will be T transpose D, T transpose RL. Okay, so we call this quantity to be stiffness matrix in global coordinates, represented by K times D is equal to R. Okay, we again got the same quantity. K times D is equal to R, where these have different meanings, where capital K, capital T, K is equal to T transpose K local times T, and R is equal to T transpose RL. You will get these things solved by solving one numerical problem. We will be solving that shortly. Okay, these are the things we have to remember. Then other things will follow, like in the trust problem. Other things, how we were able to compute other things, axial force, shear force, and bending moment. So here again, it will be same things. Axial force will be, so I will write axial force. Axial force P will be EA by L. There it was U1 minus U2. So U2 minus U1. So here we have different degrees of freedom. So in place of U1 and U2, we have D1 and D4. You remember this, okay? D1 and D4 are the actual degrees of freedom. So here again it will come my minus D1 plus D4. This is for actual force. Okay. See, similarly we can write for shear force. Shear force V of S, you know it from the beam problem that it is given as EIV x x x. Okay, third derivative of transverse displacement with respect to x. It is formula is EI by L cube, EI by L cube 12 6L minus 12, 6L. Okay, here the degrees of freedom will be D2, D3, D5, not D4 because there is actual degree of freedom, D6. There will be one more term plus QL by 2, 1 minus 2s, minus 1 plus 2s. So due to the distributed load. Bending moment, we can write bending moment ms to be equal to ei v double x. Okay, its formula we remember from dream problem ei by l square. Then there are elements in the matrix minus 6 plus 12s. L times minus 4 plus 6s. Then this is 6 minus 12s. Then this is L times minus 2 plus 6s. And we have nodal degrees of freedom as D2 to D6. Okay, plus contribution from the distributed load as QL square by 12. 1 minus 6s plus 6s square. These are the formulas for the axial force, shear force, and bending moment. Okay, we will be needing them to solve our numerical problems. So this is for shear force. This is for bending moment. Now we will be analyzing one problem, one frame, so that this concept is clear to you. So our frame looks like something like this. This is frame's one member. This frame's another member. Same member. They have same cross section. It's like this. The frame is like this, and we have fixed rigidity from both ends. This is fixed from this end, and this is fixed from this end. Okay, the loading on our frame is the loading is 1 kilopound per feet. Okay, and the data that is given is this distance up to this point is 30 feet only. 30 feet, and this is 40 feet. Up to this point, this is 40 feet, and its height is again 30 feet. 30 feet, okay. So global X is this, global Y is this. Okay, we have to analyze it. And what are the additional quantities that are given? Area of each member A is 100 inch square. I is moment of inertia is 1000 inch to the power 4, and E modulus of elasticity is equal to 30 10 to the power 3 ksi. Okay, we have to analyze this thing. This is our problem today. Okay, so first we will divide this into number of elements, looking at the configuration of our this plane frame. We can see that we can clearly divide it into two number of elements. So let us call this to be one element, this to be one element, this to be second element. Okay, and what are the nodes that will be there? This will be node 1, this will be node 2, and this will be node 3. So drawing the degrees of freedom, writing it in the nodal. So equivalently, finite element modeling of this frame will be like this. This will be degree of freedom u1. This will be v1. This will be theta 1. Okay. Similarly, this will be u2, u2, v2. This will be theta 2, u3, v3, theta 3, u3, v3, theta 3. Okay. This is the type of elements we have seen, and the elements first element is inclined while another one is having zero inclination. Okay, I will show that one also. So like this is element 1 it's inclined like this, element 1 it's inclined with global x with alpha like this x. Let's have nodes 1 and node 2. Local is like this x, and this local is y. Okay, this one again is another flat 2 3 node, and it is element 2. Only this element is having loading like this. Okay, and its local is like this, x is x, local and global are coinciding with each other. Okay, x and y. So with all this information we can easily write individual element equations. Okay, so starting with element first. Element first. So for element first, nodal coordinates. So if we choose this to be 0 comma 0. Okay, this one. Okay, so nodal coordinate x1 is equal to 0, and its y1 is also equal to 0, and x2, if you clearly look, it is x2 is this, x2 comma y2. x2 is 30 feet. 30 feet means 30 into 12 is equal to 30 feet. 30 into 12 equals 316. Okay, and this is also 30 feet high. This is 360 inches. Okay, X2 is 360 inch. I hope you got this point. And Y2 is also 360 inches. Okay, so the length of this element L will be equal to under root of 360 square plus 360 square, which comes out to be 509 inch. Okay, one more thing we have to compute sine alpha. Come up, which will be equal to sine alpha will be equal to 30 divided by 30. It will be again equal to cos alpha also. Will be 360 inch divided by 509, which comes out to be 0.707. So this is alpha actually here. Okay, alpha. This is here. Uh, this is here 30. 30 divided by 509. This one comes out to sine alpha, and this is again 30 divided by 509 comes out to be cos alpha. So sine alpha is equal to cos alpha is equal to 0.707. And one more thing, Q is equal to 0, no distributed load on this element. There is no distributed load on this element. One more quantity we will be computing, that is E by L. We will compute. It comes out to be 30 into 10 to the power 3 divided by what was L. L was 509 inch. Okay, so it comes out to be 58.93. Okay, we have to compute other things, that is other constants. A1 is called EA by L. EA by L, that comes out to be 5893, and A2 is equal to EI by L cube. Okay, this comes out to be 0.2274. Okay, I hope this thing is clear to you. Now the transformation matrix T we have to write. It's a very long matrix. Transformation matrix 0.707, 0.707, 1, 2, 3, 4, 1, 2, 3. Okay, it's like, and this is minus 0.707. This is 0.707. Then this is 0, 0, 0, 0. Transformation matrix 0, 0, 1, 0, 0, 0. This is 0. This is 0. This is 0. This is 0.707. This is 0.707. This is 0. This is 0. This is 0. This is 0. This is minus 0.707. This is 0.707. This is 0. This is 0, 0, 0, 0, 0, and this is 1. This is a transformation matrix. Okay, for turning the whole system from local coordinate system to global coordinate system. So I will directly write the stiffness matrix for this element 1. That is, first you have to compute KL. KL is given by this. It I will copy it from here. KL is given by this matrix. KL is this. KL is this matrix. KL is this matrix, and we have all the quantities. We have here, we computed here A1 and A2. Okay, A1 and A2. Substituting A1, A2 everywhere here, and L we also know we will get local stiffness matrix. Okay, and local load vector is also 0, 0, 0, 0 because there is no load. Okay, R L is also 0, 0, 0. RL is also 0, 0, 0. So directly computing, we have to multiply this transformation matrix, its transpose with this, then again multiplying by T. That is K we have to get by transpose of T, KL, this above matrix, times T again. Okay. This is like this. We will get it. The values that we will get is 2947.6, 2944.9 minus 491.05. I will take it little bit here, otherwise I will not accommodate all the values. 491.05. Then again another value is minus 2 minus 294.7.6 minus 2944.9, and last one is minus 491.05. Okay, similarly writing, because since it's symmetric matrix we will write other things. 2947.6, 491.05 minus 2944.9, minus 2947.6, 491.05. Okay, these values are 2.35 10 power 5. This is 491.05. This is minus 491.05. This is 1.1 10 to the power 5. And these values are 2947.6. This is 2944.9. This is 491.05. These two values are 2947.6. This is minus 491.05. And this one is 2.357 10 to the power 5. Okay, these are the values that we get. And this is symmetric from this side. Okay, from this side, this is symmetric. So the same process we have to repeat for element 2. Okay, okay, element 2. So for element 2, I will write directly all the things. You can compute these things at your own pace. Element 2 coordinates x1 is 360 and y1 is also 360. X2 is 840 inch. You check these things at your place, okay? And y2 is 360, okay? Inch. And length of this element is 480 inch, okay? It is sine is equal to 0, comma cos is equal to 1. If you see that alpha is equal to 0 for this element, alpha alpha is equal to 0, which is inclined like this. So alpha is equal to 0. So sine will be 0, cos will be equal to 1. So sine 0, comma cos equals 1. So clearly the transformation matrix will be another things we have to see is first it's having a q of minus 1 kilopound per feet because it's acting downwards, that's why minus, okay? So for per inch it will be minus 1 by 12 kilopound per inch, okay, because we are dealing with inches only. QL by 2 comes out to be minus 20 and QL square by 12 comes out to be minus 1600. Minus 1600 kilopound inch, okay. Another quantity is E by L comes out to be 62.5. A1 comes out to be A by L, that is A by L 5893, and A2 comes out to be EI by L cube, that is 0.2274, okay. So our transformation matrix T comes out to be, it will be an identity matrix, and because sign is 0, it is 1, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and it will be 1, 1 here. Other things will be 0, okay. This will be 0. This will be an identity matrix, okay. Then moving forward, it's a local stiffness matrix people can easily compute, okay. Local stiffness matrix is very easy, and after employing the boundary conditions, we will get for first local stiffness matrix for element 2. You people will compute it. That's very easy. Okay, local stiffness matrix, and but it's load vector RL. RL is given as 0 minus 20 minus 1600, 0 minus 20 1600, okay. These are the things in some RL vector, T identity matrix. Okay. Then for element one, once we uh, for element one, the system of equation will be applying the boundary conditions because boundary conditions u1 v1 boundary conditions this is fixed, this is fixed, so u1 comma v1 comma theta 1 0 u3 comma v3 comma theta 3 is equal to 0. All the things are equal to 0. So we have u2 v2 u2 v2 theta 2. So for element 1, our equation system will become like this: 2947.6, 2944.9, another is 491.05, 2944.9, we have 2947.6 minus 491.05, 491.05 minus 491.05, we have 2.357 into 10 to the power 5. Okay, we will be having degrees of freedom of node 2 only, that is u2 v2 theta 2, which is equal to, for this element this is 0 0 0. Okay, similarly for element 2, after applying the boundary conditions, for element 2 applying the boundary conditions, we will get the reduced stiffness matrix to be equal to 62 50.0, another element 0, and this element also 0, then this 0 3.255 and 781.3. This will be 781.3 again. This will be 2.5 into 10 power 5. This will be 0. And this is u2 v2 theta 2 again. And its force vector is there because it's loaded with uniformly distributed load. 0 minus 20 1600, minus 1600 actually, because it's from here. 0 20 minus 1600, 0 minus 20 1600, because u3 v3 theta 3 will be 0. So when we will combine these two element equations, we will get a global system like this. Global system of equations. So global system of equations. Global system of equations is, we will get this: 9198 2945 491, 2945 2951 290, 491 290 485 700. Okay, u2 v2 theta 2. Sorry. This will be with u2 v2 theta 2. Okay. and the load vector will be from this side to be equal to 0 minus 20 minus 16 unknown. So we have three equations and three unknowns. We will get the displacements to be equal to u2 comes out to be 0.003295 inch. U3 comes out to be, sorry, V2 comes out to be minus 0.009742 inch, and theta 2 comes out to be minus 0.003292 radians. This is a solution of our this uh, plane frame element. So after this, we can compute the different things. That is, we can compute the nodal displacements of each element in the local coordinate system, and using those nodal displacements, we can calculate axial force, shear force, and bending moment. I will show it for one of the element, then you will do it yourself. So you people do these things. After this, we have to calculate things for the local system, and then we will get the things for the global system as well. I think this is enough for today. Thank you. If you people have any questions, you may ask.
Excuse me.
Yeah, hello.
Hi, this is Kunal here. I wanted to check that whether you will be also covering the demonstration for on MATLAB. And,
Uh, no, I think that will not be possible. Showing you the code on the MATLAB. I will have to
okay, okay,
I'll just have to
okay,
solve you the numerical problems.
okay. Got it, got it.
Okay,
Yeah, yeah.
okay,
Thanks,
thank you.
thanks.